Welcome, everyone. Are we gonna start the meeting soon? You're still on mute, Chapman.
Okay. Good evening. Yeah. Okay. Good evening, everyone. I'm hearing sound over there. We are actually starting the March meeting of Orange County astronomers, and it's really great to see you all here. I'm the current president, Barbara Toy, in case you don't know me. And we have a great lineup of events for tonight. I should like to start by saying that we are really sorry that Raisa couldn't join us tonight. He's having connectivity issues. And we are going to do our best to carry on without his helpful assistance. Just in case you didn't notice, to do the kind of program that we do, it turns out takes at least 3 computers, which is why you see 3 computers up here. And actually, it's going to take 4 computers because our speaker has her own as well. So, we are a computer-intensive society is what it boils down to. Without more ado, we have Kyle with us tonight, and I will turn it over to him to do the announcements. And Kyle, when we're done with the announcements, we're going to be raffling off some items here before we go to the What's Up.
Okay.
Okay.
Perfect.
Oh yes. Before we go to the announcements, we had been hoping that tomorrow night would be our first Orange County Star Party since we had to close down for COVID. Unfortunately, we're having a problem with the permit process with the county, with OC Parks. They couldn't quite get their act together to get us the permit for tomorrow, so it's going to be in April. So if you were planning to go out to our new site tomorrow, please don't, but do plan to come out in April, and we hope it's going to be a really good night that time. We do still have the 2 ANSA Star parties going on. And Charlie told me, for those that are in the auditorium, if you were planning to do the Messier Marathon, he has some items down there that shows you where the things are in the sky and has the list and so on, if you want to take a look at that. So I will now turn it over to Kyle.
Hello, everyone. Let me just pull this up. Oh. Can you all see that? Oh, there we go. So, welcome new members. You can find your name badges on the whiteboard right at the front of the auditorium, or if you're joining us online after a couple months, those will be automatically mailed to you. Coffee, donuts, and water are available upstairs by the lobby for those who are in person. As mentioned, there's the next ANSA Star Party will be tomorrow and next Saturday, March 21st. Looks like they'll be doing the Orange County one in April. As mentioned, oh, do we have a issue or are we all good? I think we're all good.
And it's straightened out.
Okay, I'll keep going. Astrophysics is meeting March 20th at 7 p.m. at Orange Coast College. The beginners class is April 3rd online. Uh, Astroimaging has their online discussion group, which you can see at the link below, and the next board meeting will be online on March 22nd. The annual trip to the Owens Valley Radio Observatory is happening the weekend of June 13th. Star party the Friday night, June 12th, and then the tour and activities of the site, followed by a star party that evening on Saturday the 13th. Is Doug there, and does he want to say anything or no? All right, I'll take that as a no, and I'll keep going.
This month. How about next month?
Yeah. Uh, As mentioned, the Messier Marathon will be happening at the March 21st Star Party at Anza, so feel free to come out, and we'd love to all have you join. The club's Adopt a Scope program is continuing to run. You can find more information here on the website, including a sample adoption agreement, along with more information about the program and a inventory of what is available. Our outreach events coordinator is Martin Christensen, and please reach out to him if you can help at either of these upcoming outreach events.
Excuse me just a moment.
Yeah.
Martin, you said one of the events had to be canceled? Okay. Unfortunately, the March 18th outreach event had to be canceled. So if you were planning to come out for that, please note that on your calendar. But the March 30th one is still on calendar, right? Uh, okay.
Did you keep going?
Okay. What he said was he received an email saying that the 30th, March 30th one, apparently they think should be starting at 6:30 and ending by 8:30. And which, given daylight saving time, means that it's not going to be much of a viewing event. So keep keep an eye out for further messages regarding that.
All right. The Dave Fisher is the editor of the series Astronomer. If there are any items of interest you think would be good to be featured in the newsletter, please reach out to him. His email is newsletter@ocastronomers.org. Items we look for are articles, images, trip reports, club news, etc. Friendly reminder to all those who are out using the ANSA site. Uh, if you're the last one to leave, make sure to lock the ANSA house, ensure all windows are closed, and close the gate to the site as well. Additionally, please keep your pad clear of weeds, and if you can help out in the common areas such as the ANSA house, football field, and the observatory, that would be very much appreciated to reduce our fire risk. The next general meeting will be April 10th, and then we're going to move to the raffle.
Much, Kyle. And let me see. You have a couple of bags of books here that are going to be raffled off, and also a Celestron power tank that was donated by a club member. So I will turn this over to Mike. Are you doing?
Oh, nope, nope. I'm going to be the product model. So we have some great comic books here. There's 3 of them. How beautiful they are, and also.
Do you want the microphone for that?
Sure. How beautiful they can be, and how they can also kill you if they hit us in the wrong time. And then we have some star atlases. One of those is deep sky objects. One of those is a star atlas. And I believe we have another one that is just lots of pretty pictures. And then we have a Celestron power tank here, which is, complete with a lot of battery capacity and a light, and which helps you out in lots of different ways when you're doing telescope observing in the dark.
Start out with the comic books.
Comic books. comic comets.
We're going to take, you're going to choose a number between 1 and 100, not including 1 and not including 100. And whoever gets closest to the number that I have chosen without going over it will win.
And I don't win.
You don't. So you get to help keep track of the numbers. Closest without going over it. Okay. Who wants to start guessing? 42. 27. 50. 38. What? 67. Anybody else? 89. 70. 25. All righty. 64. Anybody else? Give it a shot. Okay. 77. Anybody else? 46. 71. Is that it? Any other guesses? Do you remember who had it?
You had 27.
Right there. You got it. Come on down.
Oh, I'll get you.
Do I need that?
Well, we're going to do this again, right? All right. What about the people online?
Sorry about that. Forgot about that. Okay, here we go again. Same thing. Between 1 and 100, not including 1, not including 100, and whoever gets closest to it without going over. Okay. 42. 42. What? 99. 18. 25. 58. 8. 62. 13. Anybody else? 7. 50. 57. 67 again, right? Okay. All righty. Anybody else? Did you catch who it was?
Who said 45?
You got it. 45. Way to go. Okay, last one.
Yep.
Here. Okay. All righty. Same rules, same game. Let's do it. Hands up. What do we got for numbers?
Sticking to my gun. 42.
42. 67 again? Okay. 28. 33. 99. 66. 46. 39. 51. 28. 11. Here we go. 81. 31. 32. What's that? 56. Any others? 51. Last chance. That's an easy one.
Sure is. We have a clairvoyant in the audience.
81. 81 did it. All righty. Congratulations to those, and thank you all. Appreciate it.
Thank you. And before we go to our What's Up program, Jake, would you please see Don Lynn at the end of the meeting? Oh, Don Lynn is over there. So you need to see him after the meeting, and you have an announcement?
Yes.
Okay.
Real quick.
Here.
There is finally an update to the inventory, the club's inventory. It was posted this morning, so you might take a look at that under the Adoptoscope heading on our website.
Don Lynn over there. Yeah. Okay. That was Jake with the announcement about the update on the Adopt a Scope program. And now I believe we are ready for our What's Up program. And we have returning club member Mike.
Hey, everybody. Good to see you. We'll get that presentation up. Good to see everybody again. We had a nice room full tonight. So what'd you learn in school today? What's that? Oh, okay. Here you go. Got to load up the presentation here. Should be able to run it right from that thing if you can see it. How about this hot weather, huh? I was out testing some of my suggestions last night, and the only reason I wore long pants is a fear of mosquitoes. Do you want to? Almost there. Do the there. That note there. There you go. All right. Thanks a lot, Alan. Okay, let's get going. So I'm really happy to be here, and I know I've said this before, that this doing these What's Up presentations really gives me an opportunity to, do as a lot of, as you might say, when you have to teach, it's a great opportunity to learn. And so every time I do one of these, I spend probably about 10 hours just thinking about things that I might like to share with people, and I learn a lot along the way. Oh, we got oh, great, fantastic. So number one, doesn't it feel like summer? Well, it's not even vernal equinox yet, which takes place on March 20th at 7:46 a.m. Pacific Daylight Time. And the thing I always keep an eye on when it comes to these presentations and talking about equinoxes and solstices, how much time dark sky time do we have, or astronomer friendly time do we have? And it's definitely going down. We're down to about 10 hours of real dark time. But if you contrast that with what we're going to see in June, when we'll only have less than 7 hours of real darkness, we better get on it if we're going to enjoy the night sky. And that's in part why it's a good time to do a Messier marathon. Moon phases. So this morning I went out, there was a beautiful blue sky, and I saw a nice moon getting very close to new, beautiful in the morning sky. New moon's on the 18th. We have a full moon on April 1st. And, oh, got it. I think so. More should be a hide. Oh, there you go. Thank you, Barbara. I really appreciate that. And all right, great. And what I like to do is this. I usually use this to help plan when I'm going to observe. And I have some rules that I came up with that I live by. And best dark sky observing for me is really when the moon rises, um, so late that I don't care, or it sets so early that I don't care, as in terms of affecting my evening viewing. And so the best moon viewing time is kind of the converse of that. I like to look at and show people the moon between about 4 and 10 days after new, because you get a lot of nice terminator action going on. And it's a really great time to view the moon. There we go. There we go. Now, the full moon on April 1st has a number of names, but the most common, I used to fight, giving all kinds of fancy names to full moons. But the most common names that came up in looking for a fun common name for the moon in April 1st is the pink moon or the Paschal moon. And when you think about it, Easter is actually triggered by when the full moon happens. And so because it's the full moon right after the spring equinox, it determines the date of Easter, which is April 5th this year. So I love to look at the moon, and I always love to share something that maybe myself or others haven't heard before. But when we look at the moon, some things that immediately stand out as noteworthy when we're showing people are the craters Copernicus and Tycho. Tycho, of course, a great astronomer who took such accurate positional measurements of the planets that later astronomers such as Kepler were able to derive planetary laws of motion. Copernicus, of course, famous for the sun-centered solar system model that we cherish today. And these scientists both worked in the 1500s. And I always love to throw in the Apollo 11 landing site in the Mare Tranquillitatis, or the Sea of Tranquility. But I like to look for something a little bit new. And so in doing a little bit of research, I came up with craters named after Aristotle and Eudoxus. And both of these philosophers lived in around 350, or they did their work around 350. And they came up with very elaborate Earth-centered models of how to explain planetary motion. Of course, we know that's wrong today, but they thought a lot about it. And then the crater Cassini, of course, we think of as, Cassini's division being named after this planetary astronomer. Really nice grouping right above the Sea of Serenity, and best observed between about first quarter and maybe 10 days in. So I actually haven't looked at that myself and scrutinized that area, so I'm going to do that. This is just an okay month for planets, for bright planet viewing. This chart basically shows darkness and sunshine, and the yellow bars in darkness are when the planets are visible. So you can see that Jupiter is visible, very visible now up until past midnight. But all the other planets, all the other bright planets are kind of in Never Never Land. The one exception here is really Mercury is going to be at greatest western elongation, meaning it will be a morning object just above the eastern horizon. Greatest elongation is on April 3rd. And an interesting point here is that Jupiter has been drifting its way across Gemini in retrograde motion, and retrograde ends on March 11th. So it's going to stand still in the middle of Gemini for a while and then proceed eastward. A few things going on here to make note of. We have a nice planetary lineup, and I'm not calling it an alignment, but it's a nice little alignment. On the evening of March 21st, which is a nice star party night, it's a Saturday, we've got Venus, a thin crescent moon, the planet Uranus, which is worth looking at, and the planet Jupiter, all in a pretty nice lineup, right as the sky is fully dark. Then we have a couple of nice conjunction nights on the 25th and 26th. The moon will be really close to Jupiter, and in the constellation of Gemini. Again, beautiful evening object, evening appearance that you should all, strive to see. And you can also maybe use this as a chance to start saying goodbye to the winter triangle formed by Procyon, Sirius, and Betelgeuse. Some of my deep sky picks for the month, not surprisingly, are going to focus on galaxy season. What is galaxy season? Well, as the Earth goes around the sun, the evening sky either points toward the galactic center or away from the galactic center. And at this time of year in the evening, we are facing out through, perpendicular to the galactic plane. And so we have a chance to see lots of distant galaxies that aren't blocked really by the Milky Way in the foreground. And, really when there's a bunch of Messier galaxies in the eastern sky, and it's, still not summer yet, so we get a lot of darkness, it's a really great time for the Messier marathon. And so galaxy season is right now, and now that there's a new moon, it's a perfect time to start trying to find all the Messier objects in one night. Just for fun, the Messier list is 110 objects, and it's topped by galaxies. And that kind of makes a lot of sense because Charles Messier was a comet hunter. He looked for fuzzy things. And I was a little surprised when I tallied it up here that nebulae really only account for 10 of the 110. And galaxies lead the list because they are the faint fuzzies that can fool people, in my opinion, the most as being a comet. So a little bit of Messier marathon strategy. You want little or no moon. And so now that's the 13th through the 21st. Tonight would be a great night if you were in a dark place. The next opportunity is mid-April. We need a clear east and west horizon. You got to catch objects right after sunrise and right after sunset and then before sunrise. And if you're going to sleep and you intend to get up, you need to plan that pretty carefully. As Barbara said earlier, there's a really nice list on the OCA website, which was written for the 25 Messier Marathon. And looking at that, it's absolutely applicable and a wonderful guide to help you do that. So now in the eastern sky, and for the month ahead, we have a nice grouping of those constellations from Virgo through Leo up into Cancer and Gemini. And for those of you who haven't heard this is old news for astronomers, but you follow the handle of the Big Dipper and you arc to Arcturus and you spike or sail to Spica. And that kind of defines, helps you remember what you're looking at. Now, when I was a kid, I can remember looking at a star chart and seeing on there that it had an area labeled as the realm of galaxies. And I remember when I was 11 or 12 years old, that really excited me to think, oh my God, there's like tons and tons of galaxies there. And so I thought tonight I would point out a few things that are part of that realm of galaxies that's really bounded by Coma Berenices and Leo and Virgo. But before I dive into the deep sky here, I want to point out that the Coma cluster, which is also known as Colander 256 or Melotte 111, is an absolutely beautiful open cluster. It's a little further away than the Pleiades, and it's gorgeous. So if you're not out in a dark sky place, this is really, really visible. Now, let's start with a few cool things. And what I did here to parse these was I looked for high surface brightness galaxies that you might have a better chance of finding and also might be a little bit more photogenic. Messier 49, giant elliptical galaxies, a galaxy. And one of the cool things about it is it's estimated to have a supermassive black hole with a mass of over 500 million solar masses, which just kind of blew me away. And it's also estimated to have over 5,000 globular clusters in it. Now, our Milky Way has, less 200-ish, maybe a little less. So it's a massive galaxy, and it is actually within the realm of binocular vision with a dark sky. Another one is Messier 58, and notice the location of these galaxies. They're all kind of in the arc of Virgo, and they're really close together. And I got to tell you, I haven't looked at all of them. I've looked at some of the ones that are better known. Messier 61 is a face-on spiral, 58's a barred spiral. So you get a nice sampling of the different galaxies. Most of these are Seyfert galaxies, which means they have an active galactic nucleus, well worth looking at. You can see by the magnitudes, if you have a telescope, these are well within the range of just about any telescope. And then if you're actually, these are beautiful pictures I've pasted in here, But if you have a decent, telescope of a few inches of aperture and you're out in the desert, that's more like what you're going to see. It's not going to be a beautiful, colorful image. It's going to be shades of gray, but well worth studying. Messier 90 is what's called an intermediate spiral. Some debate as to whether it's a Seifert truly or not. It's fairly quiet. And also, again, in that same close area of the sky. Now, think about this. This is a little 3-degree field, which is pretty small. It's about half the width of a binocular field. There are 15 galaxies within the reach of a modest telescope in this small field. And that's what we mean by the realm of galaxies. And if you start with Messier number 86, which is an elliptical, and kind of work your way, slowly panning the area, you can look at Markarian's chain, which is just a lineup of tons of galaxies, all in a really tight spacing. So for you astro imagers or people using telescopes with automatic imaging, these are some of the great targets you might want to try. And I would be remiss if I didn't mention the Leo triplet, which is Messier 65, 66, and NGC 36, 28, one of the most popular galaxy groups, right at the tail of Leo, the Lion, so pretty easy to find. I love carbon stars, and Cancer, which is in that lineup in the realm of galaxy area, has a really beautiful one called X Cancri. It's about 1,800 light years away. And last night, I was using my 10 by 42 Canon binoculars, and if I put the Beehive star cluster on the right edge of the field, I could just see this beautiful orange carbon star on the eastern or left edge of my binocular field. It really is orange. I tried my own advice before I put this here, and you really ought to take a look with a pair of binoculars. Even from the city, the Beehive is a beautiful cluster. A little bit about a couple more. I think this is close to the end of my slides. Taking a close look at Leo the Lion, Regulus is actually a 4-star multiple star system. It's 4 stars in 2 pairs. Now the separation between those visible stars is really wide. It's like 3 arc minutes, but it's worth taking a look at if you haven't. And even more interesting is Algeba or Gamma Leonis. Gamma Leonis is 2 stars, very bright, 2.3 and 3.5 magnitude. The brighter star is a K-type star. It has a known exoplanet. And so if you ever want to show somebody a star that has an exoplanet orbiting it, it's a really good one to pick. So some dates to remember. We're in the best time to try Messier Marathon, nice dark of the moon period. 21st, that thin crescent moon above Venus and the planet lineup. First quarter moon near Jupiter for 2 nights. And then look for the famous astronomers' craters on the moon, which is something I'm definitely going to do. And then Mercury is at greatest western elongation on the morning of the 3rd. And that'll do it. And I will say that there's my email. It's michael@discoverthestars.net. If you have any feedback or you would like to suggest anything you might want to hear about in a future What's Up, let me know. And with that, I'll say thank you.
Thanks a lot, Mike. We really appreciate that, and gave us a lot of things to look at or think about. Sorry, I'm at the stage in my eyes where I need assistance at times. This is the time we're actually for our main speaker, and I'm delighted to introduce Elena Murchikova, who is an astrophysicist who's interested in black holes. She's currently an assistant professor of physics in astronomy at Northwestern University and was originally from Moscow. She holds 2 PhDs, one in astrophysics from Caltech and another in particle physics from Moscow State University. She completed her postdoctoral studies at the Institute for Advanced Study in Princeton and at Harvard University's Black Hole Initiative. And then outside of research, which it sounds like is probably taking most of her time, she enjoys mountaineering and also drone photography. So there are all sorts of other things one could ask her about too. However, tonight she's going to be talking to us about the Milky Way central black hole and lessons on accretion physics. So please welcome Elena Murchikova.
I think it works now. Yes. Thank you so much for inviting me to give a talk here. It's a great pleasure to meet many of you. Spectacular. Okay. Thank you very much for inviting me to give a talk in this wonderful meeting. It's a great pleasure to meet many of you. Today, I'll talk to you about black holes. First, we'll talk a little bit about what black holes are in general. Then we'll talk why they're important in the universe. And then we'll talk about our own galactic center black hole. I probably prepared too much material, so we'll just stop where we stop. Okay. All right. Let's start with a brief history of what the black holes are. As many of you know, as I guess all of you know, black holes are the consequence of general relativity. Einstein discovered general relativity and published it in 1915. And soon after, already in 1916, Schwarzschild and separately Droste found so-called Schwarzschild solution, which is what we now call a black hole solution. There is only 1 year gap between those two, and it might sound very impressive that it only took a year. The truth is, of course, that Karl Schwarzschild at the time was calculating the projectiles in the First World War. And so he was doing it in his spare time between doing whatever he was doing in the trenches. The name black hole did not appear until much later. And in 1916, the term was coined after, which is very depressing, it was after a prison, Black Hole of Calcutta. And a little bit later, John Wheeler decided that that sounds really nice. And for advertising value and brevity, black hole became black holes. Okay, so what is a black hole? Can I ask an audience? Go ahead. Well, you're telling me how it is formed. I'm asking what is the black hole? Singularity is in the middle. What is the black hole? That's a good one, and that's the one I was waiting for. Thank you so much. So that's what we usually say when we give talks. Like, that's what I would usually say when I give talk. Until a few weeks ago, I was talking to someone who brought a very good point up. That's exactly what you just said, right? So we take Earth, we launch a satellite on an orbit close to Earth. And we can calculate what's the velocity it needs to be to stay on this orbit, and to be precise, at 7.9 kilometers per second. And we know that if we give a little bit more velocity to the satellite, it will just escape Earth and flies away. And so we know how much velocity we need to give to an object to escape gravity of Earth. Now we can imagine this experiment. We making Earth more and more massive. Oops. We're making Earth more and more massive. And we get thank you. And we get to the point where this velocity becomes speed of light. And we know that we cannot give it more velocity to escape, because it can't, because we can't speed anything up to the speed of light, or definitely not high. But unfortunately, none of what I was saying is a consequence of general relativity. This is classical Newtonian mechanics. So this object, which would be very massive, that something cannot escape, only light, even light cannot escape, was actually known back then to Newton. Who would say, well, I can imagine a star, which is that massive that light cannot escape the star. And obviously they didn't call it black hole back then, but nothing here actually has anything to do with general relativity. So what's the truth? What's actually black holes? So black holes are, it's actually a very abstract thing, right? So when Einstein was figuring out general relativity, they are based on assumption that the mass should be curving space and time. So Schwarzschild solution is a solution of the following problem in general relativity. I have a point mass at the middle of my reference frame, and I want to know how the space is curved around it. What does it have to do with anything about gravity? Is because when space is curved around it, the behavior of particles flying past this object are such that it looks like they're subject to gravity. Questions, concerns? I would love you to interrupt me while I'm talking, because it's just easy. If I lost you, you tell me, and I will do my best to undo it. There is no fundamental limit on that. You can say like the smallest mass you can imagine. There is no limit fundamentally on how to do a black hole. Any more questions? Have I lost everybody already? Great. Let's move on. So what I was just saying to you about black holes is very abstract, right? Some solution of four-dimensional equations. And it just happened that we're lucky that at larger radius, they behave exactly as you would expect from Newtonian mechanics. Your particle moving there feels attraction. But as you probably know, they behave this nicely at large distances. But at small distances, they're really weird. They're kind of your mass, which is point mass. Well, and technically it can't exist because it's a point mass, is punching holes in the space and time. So the solution has been known for a long time. I mean, it was interesting, but was mathematical curiosity. Until the biggest contribution of Oppenheimer to physics is that Oppenheimer figured out that if you have a very big cloud and you let it collapse under its own gravity, what it will go to, if you do it in general relativity, what it will go to the Schwarzschild solution for the black holes. So Oppenheimer figured out that you can make black holes not only on paper, you can actually make them in space. Because universe does not have a lack of clouds which have opportunities to collapse. So later, quasars were discovered, and objects, quasars which are known to be very big and massive black holes in the centers of big galaxies, and also stellar-sized black holes been discovered. This was in 64, and it's a black hole feeding from the star and orbiting it. So from mathematical abstraction, we moved to understand that a black hole can be everywhere, because a small cloud can collapse to the star, a star can collapse to the black hole. And if you have something really, really big and a lot of time, you can probably force something much bigger than a stellar-sized black hole. And those guys would be living in the centers of the galaxies. So we know by now that there is a black hole in the center of every large enough galaxy, where large enough is defined larger than the Large Magellanic Cloud. Yeah. Anyway, why do we care about black holes? You know, mathematical curiosity sitting everywhere. Of course, they're cool and nice and interesting because, you know, black holes and punching of space and time, time turning space, space turning time. But why do we care about it in astrophysics? You see, black holes are kind of big attractors. They're massive objects, meaning lots of stuff can be stuck next to them. So essentially what we usually say, they create a large potential well. And if you have a large potential well, it gets filled with junk, with a space junk, which is in this case, gas, dust, stars, whatever is floating, ending up close to the black hole. Most importantly, gas. So when material accumulates in one small area, and there is a black hole in the middle, and so it has to orbit, material collides with itself. And you have a lot of dust, the gas collides with its, you know, one cloud collides with another cloud, and it loses a lot of, on this collision, it loses velocity. So it starts moving closer to the black hole. Amount of material closer and closer is getting more and more and more denser and denser. So there is even more friction. So when material experiencing friction, what happens? It's getting heated up. So you have hot gas orbiting around the black hole, and it radiates. And that's what we call black hole emission. Black holes themselves, from the point of view of astrophysics, there is like no Hawking radiation here. There is no hope for it. From the point of view of astrophysics, black hole emission is emission of gas orbiting the black hole. If I would ever use this term, I explicitly mean just the gas around it, not the black hole itself. And so there's a black hole, bunch of gas, it's all orbiting, getting heated, radiating. And turns out, during that process, the amount of radiation you can receive from the black hole is comparable to mc square of material falling into it. Everything which ever scales as mc square is enormous. For example, early atomic bombs explosions worth about 40 grams of mc square. It's nothing. Black hole produces, as a result of this process of accretion, what we call it accretion when the gas orbits it and falls and emits. In the process of accretion, black hole produce a lot of radiation. If they produce a lot of radiation, they also dump a lot of radiation around themselves. Small black hole dump this radiation in, you know, smaller areas from themselves, big galactic center black holes can completely obliterate their own galaxy. They can expel all the gas from it. They can kill star formation. They completely shape their own galaxies. Well, and if the black hole is small, then you can have star formation, you can have other things. So depending on the relationship between black holes and a galaxy, the galaxy can look completely different. So the black holes actually playing the central role in the universe. We often call them engines because of how much energy they produce in this process of accretion. Questions? So Hawking radiation is much weaker. So what we're talking here is just Hawking radiation is usually, when you discussed, is a black hole in a vacuum. So essentially, there are particles appearing close to the horizon and not being emitted from the black hole. Number of those particles incredibly small. In real situation, you don't have a black hole in a vacuum. You have material. As soon as you have material, that's what dominates. Because it was just the tiniest correction, there is absolutely no hope of detecting Hawking radiation from an astrophysical black hole because of how much junk is floating around it. The light comes from the material orbiting it. Then you can image thing closer and closer and closer, and then you can figure out where it's coming from. Yeah. You can save through light along. Like for example, you can tell the difference if the galaxy is powered by the black hole or by star formation, because when stars are formed, the stars doesn't matter how complex they're essentially a black body of a given temperature. And the black body have a certain characteristic behavior. Black hole emission is considerably more hard. There is much more high energy particles which stars cannot produce. For example, stars barely can produce double ionized helium, which would be 56.6 EV. Like that's how much you need just to ionize helium twice. And stars can barely produce anything. Black holes can produce a lot of that. You can pretty much detect if it is a black hole or a star by if you see double ionized helium in your surrounding. Like you can figure this out. Oh yeah, of course. Well, further down. Okay. All right. No problem. I'll do this. Yes. Go ahead. The question was, there is a c, which is the speed of light, and there is a c square in mc square. And what does it do in there? Because why is it c square? Yes. So mc square, I mean, that's dimensions, right? Like, as we know, we can't compare dimensions of length to time, things like this. C has dimension of velocity. While particles supposed to have dimension of energy. remember mv square by 2. Kinetic energy of a particle is mv square divided by 2. So it takes 2 velocities to make energy. So we're talking about fundamental energy of a particle of mass m, right? Which can be anything. You don't have any other quantities at all. So you have mass and you want to make energy. You can only use fundamental constants to pair this mass with. So you multiply mass by fundamental constant c twice to get energy. Otherwise, the dimension is going to be wrong. Am I explaining? The speed of light is, fundamental constant.
There's a question is how can gamma ray bursts escape the gravity of black holes?
Because depends, because it's happening outside the event horizon. So that's why you escape. Like you cannot escape from inside, but you can escape from the outside.
And the next question is, does gravitational redshift affect gamma rays to the visible light spectrum?
Yes, because when you escape, black hole forms your potential well. Depends how deep from it you're escaping, you're redshifting when you're getting out. So because you need to spend energy to get out. So you have given energy, which is, I don't know, blue light, and you subtracting energy while you're climbing out. And so you shifting your spectra to red. Any more questions? So the question was whether the black hole, whether the solar system is bounded to the center of the gravity, or the center of the galaxy with the force of the black hole. It's a very good question, and I even have a slide about it. We just talked about this, that the black holes are dumping lots of energy, because I'm just directly going to that slide. And so would like to clear some of the misconception, because this is a very fair point. Because often tempting to think that the black hole is bounding the galaxy together. But the reality is it's not the case. So galaxies are formed inside dark matter halos. There's a very massive halos. It's like also big potential well. Nature of dark matter we do not know, but we know it's there. And the galaxy forms in those halos because it just attracts more material. And the black hole happened to be just the heaviest, particle of all those, and it tend to sink to the center of the galaxy as a result. So no, they're not bounded. Black holes effective, like for example, sun is located at 8 kiloparsecs away from the center of the galaxy. 1 kiloparsec is about 3 light years. So it's like 24 central light, 1,000 light years from the center of the galaxy. And the black hole dominates only inner 1 light year. So everything else is like just the bulk of the stars, clusters, and more material, and starting dominating very soon away from the black hole. Our own black hole is particularly small. Nada.
Another question is, do you think gravistars are real?
Gravistars would be, what's the definition of the gravistar? So then I would ask you for your definition of gravistar, and then I'll answer. You can type it back in the chat. Thanks. Sorry. All right. Bonding. If I missed any more questions, please shout at me. So one potential misconception was whether black hole binds the galaxy. The other one is how do black hole disks around the black hole look like? Because if you just go in the internet and search for a disk around black hole, what you get is approximately this. The top one is an interstellar black hole with a red shift and blue shift added back to it. And the bottom one is just some graphic from NASA GPL or a press release. So what you see is a black hole and something thin around it, right? This is how we usually visualize environment around the black hole. Well, we can take it a step further and say, well, this is a Saturn, but that's an accretion disk around the Saturn. So Saturn rings are accretion disks. Is in the same way as the disks around the black hole, a feeding black hole, Saturn rings are raining into Saturn. And they're also thin. So this is unfortunately that when you get a thin disk is only true when you have a lot of material. And let me explain why. So probably you seen several times. I will explain what else is written on the slide. But importantly here is that when you see simulation of a black hole, you see something like this, which is, well, hard to even say where the disk is because it's just something red and it's everywhere. When, when we look at the movies and we see something very thin. So what's the difference? The difference is like this. If you have a lot of material, you have a black hole, it's all orbiting, you have a lot of material there, your protons and electrons meet each other very often. They collide from each other. Electrons are light, and they are primarily responsible for radiation because they're light and they charged. You kick electron a little bit and it radiates. So protons are very massive. And while they also collide, they tend to very little go away from their trajectories, so they radiate much less. So what's important is that at some point close to the black hole, everything is ionized. You have separate electrons and separate protons, and they continuously collide with each other. Electrons radiate, they cold electrons meet again, they all own hot protons, they collide with them getting hot again, I mean electrons, right, radiates again, and electron kind of wasting the energy of the system into light. When there is not much motion except orbiting, and everything tends to settle into nice thin disks. Because everything which will be perpendicular to the disk will collide with the disk and die. This motion will die out very soon because bunch of collisions and it's all nice smooth disk. What would happen if you don't have much material? Your electrons and the protons would really love to meet each other and exchange some energy and radiate. But electrons and protons just it's so thin, they don't meet each other very often. Electrons radiate away most of their energy, and they don't have enough collisions with proton to take their energy away. As a result, you are unable to cool the system. And instead of thin disks around the black holes, you have something incredibly thick because your motions are not only in nice plane, but also all over the place because everything colliding with itself. So when we talk about accretion disk and about black holes, they not necessarily looking like disk. It can be something with an opening angle of 180 degrees. It's pretty much just a hole, and it takes the rest of the volume. It can be confusing, but there is a lot of simulations about that. One of the big issues with black hole astrophysics is that there are so many processes involved in describing the black hole accretion and radiation that no pen and paper theory is possible, because nuclear physics is important, radiation is important, molecular physics is important, plasma physics is important, general relativity is important, everything is important. We'll talk a little bit about this a little later. Any questions on that part? Go ahead. Don't worry about this. Advection and when just this material just moves inward, kind of moving in. That's it. It's just for moving. Okay. All right. Let's move to our own Galactic Center black hole. Actually, yeah, let me ask again, any more general questions about black holes before we move to Milky Way? See. There are galaxies which have companion double black holes at the center. We usually believe that it's because two galaxies collided and two black holes got stuck with each other. For the stellar sized black holes, we assume that's common. We haven't seen them because they're small and hard to see. What we definitely know that majority of stars spend majority of their lives in pairs, particularly massive stars and the stars which are making black holes. So problem can happen when one of them explodes at the end of the life. So, and that can kick out the other star. So you need to be lucky to keep the second star and let it go into the black hole again. But yes, double black holes are absolutely common and they're everywhere. Go ahead. As far as we know, all massive galaxies, which more massive than Large Magellanic Cloud, I see. So there are galaxies which can have even smaller black holes, like not a million masses, but like 100,000. So you see, finding a black hole, it's easier to find black hole and prove it's not there, right? Because when you see black hole, you know what rotates. You can do the best you can and say that whatever there is, if it is a black hole, it's smaller than certain size. There are claims of the galaxies which don't have black hole, but fundamentally, it's very hard to disprove the presence of the black hole. You can only set the limit on its mass. Because it's hard, right? Like you can't really fly there and check, but you can always figure out if it's there when it's there. Yeah, it's a great one. So yeah, the black holes would be roaming around the galaxy as well. So there are free floating black holes, there are free floating planets, there are free floating black holes. There are statements of like, there are claims of supermassive black hole being ejected from the galaxy and just floating by itself. So yeah, you can kick those things out, especially if you have kind of interaction with something else. All right, oh, sorry.
The person who asked the question about a gravastar, his definition of a gravastar is a star does a supernova almost, but not achieve black hole. The massive material is left and forms dark energy with negative energy. Gravity is pushing in and dark energy is pushing out.
So you're trying to form a star out of dark matter. So there are statements, there are theories which are discussing forming stars or black holes out of dark matter. It requires certain condition on the dark matter. Obviously, because we haven't detected dark matter, possibilities are really wide for speculating on that topic. We haven't seen anything in the in the universe which would look like that. Whether it does not exist, the universe is big. Who knows? I would, if I was betting, I would say no. But it's my personal opinion. Physics is bigger than me. Have I missed someone? I don't think so. Okay, let's move to the Milky Way. So, Milky Way galaxy also have a black holes in the middle, because it would be strange if Milky Way galaxy was very special. So, Milky Way is a spiral galaxy, as you know, and it's an artistic vision how it's supposed to look like. And the sun is at about 8 kiloparsec away, and as I say, 1 parsec is approximately 3.3 light years. So we know that there is a black hole at the center, and I'll talk about this image a little bit later. So how do we know there is a black hole? Our own galaxy is probably the only place we can actually prove it. Because stars in the Galactic Center has been tracked for, by now, more than 25 years. And you can see how stars are moving. So this is a movie from the Galactic Center group in UCLA. And those stars are actually stars which have calculated trajectories for them. So what you're looking at is a so-called S cluster, is a group of stars which are closest to the black hole. We'll return to some of them later. And when you see the tails, like that's, you see the star moving because they are moving on the imaging. Okay. All right, this is from UCLA. This is also from UCLA. That's the previous one was three-dimensional, obviously. This one is more observational. That's what you actually see when you stare at Keck telescope. You see the dots moving. The star in the center is where Galactic Center black hole is supposed to be. And the motion of the star is they are shifting. And there's another one is with gravity, which is led by Max Planck Institute in Garching. So you see a dot is moving. This is not a simulation, this is an observation. When they put a dot, that's where they see it. So what we know about our galactic center, that we track the stars, and we know there is something at the center around which they're orbiting, which is so massive that it curves the star trajectory that much. And it's also very small because we see the stars passing really close to it. It's so small and so massive that it cannot be anything else except a black hole. So that's the only place where you can absolutely certainly prove it by just visual trajectories of the stars. That's another one of the passage of the star which passed the closest to the black hole in 2018. The next passage is going to be of a different star, is going to be about 8 years. Okay, let me fly you in the center of our own galaxy, so we can see how our black hole is living, what it's surrounded by, and what its life like. All right, Galactic Center is the best visible from the southern hemisphere. It rises here, so we see it from the northern, but it's really beautiful from the southern. So there, in the constellation of Sagittarius, from where it takes its name, covered with thick dust clouds, on the side of this very obscure region, and just a little bit, I don't know if yes, you see my mouse. So right here, this little dot, we're going to be zooming in. That structure is called the mini spiral. Just on the side of this mini spiral, there is a black hole. So I will build you this region structure by structure, so you'll see how complex and interesting this is. So this is a black hole in the center. East and west is in wrong direction because that's a convention, because that's how it always will be, because that's how it started many years ago. Because of the plates, you take an image and then you look at them the other way. A variable radio source was detected. And when I say variable, I just mean the light from it changes. And so here is an example of how light from it changing on the time scale of, this is a 60 minutes. So it actually changes on a time scale of seconds, you can see it. Variable source, which is we are associating with the black hole, which is 4 10 to the 6 solar masses. 4 million solar masses. It's surrounded by the nuclear star cluster of another several million of solar masses. And I will overlay on top, that's a nuclear star cluster. It's a very, very dense region. This is the galactic plane, and I will have markers everywhere here, rotation markers. So if it is a dot, it's coming toward you like an arrow. If it's cross, it's the end of the arrow. It's coming away from you. This is the rotation of the galaxy. So it's coming here from the bottom, goes like this and goes away. That's a structure I already showed you. Is a mini spiral. I'll blink it back and forth. This is an observation of it. It's a free streams of gas, free streams of ionized gas. It's very hot gas. The temperature is comparable to the temperature of the sun. 10,000 Kelvin. Free streams, they're also rotating. So the one from the top go behind me and comes back here. The one which is almost horizontal is going away there, right? It comes back here. And the other one, we don't know if it is rotating because it's maybe in the plane of the sky. So this is the mini spiral. It's surrounded by very massive ring of molecular gas, and I will again blink it. That's the ring of the molecular gas with rotation. Red shift away from you, blue shift toward you. This is molecular gas, so it's between tens to a few hundred kelvins. It's pretty cold. And it's also rotating. And you can see that the top goes away. It's going like something like this. And it comes here. That's the gas. Can I help you? You have a question. I'm going to answer your question. I'm talking about structures around the galactic center black hole. Do you have more concrete questions? There's just lots of them. I'm just naming them one by one. Am I confusing everybody? Please raise your hand and please ask me a question. Go ahead. It's a good one. That is a lost opportunity because instead of something like shark in the sky, they called it circumnuclear disk, which is really depressing. Shows the lack of imagination. And by the way, the black hole is called Sagittarius A star, with star not for like a star like an object, but because Sagittarius A was already taken. It's an asterisk. Sagittarius A star with star standing for asterisk. It's also lack of imagination. There was a question, sorry. No? Oh, yes, you. Yeah, yeah. Yes, but we also, we know it's kind of circular. We do know orientation from other structures, which we know in front and behind. So that helps. Otherwise, you wouldn't know which direction it's oriented. Yeah. But there are structures where you can see more gas here, less gas there, so you know how it's oriented. I'm just naming a bunch of structures which are in the galactic center, of which there are many. There is another thing appeared in the purple at the center. It's a group of young stars just sitting there orbiting. Very young stars. I will bring this point a little bit later among the mysteries of the galactic center. That was what I previously showed, like molecular gas, ionized gas, but it's all swimming in the sea of really, really, really hot gas, like X-ray emitting gas of 10 to the 7, 10 million Kelvin. It's all filling this region. And everything I was showing you was to scale. So this is a structure I was showing you before. You can see that you can barely see anything from it, except there is a little bit of anti-correlation where it is and where it is not. Like at the center, when there is nothing, you see more X-rays. All right, it's getting worse because you can get closer to the black hole. And there, you can have this S cluster, which I showed you with a bunch of stars orbiting. Those are the most tracked stars probably anywhere in the world. And that was for tracking of the stars and discovering that this is a black hole. There was a Nobel Prize to Andrea Ghez, who is at UCLA, and Reinhard Genzel, who is at Max Planck in Garching. Those are the stars which I showed you before. The star which I showed you the passage of is this little blue thing right there around the black hole. That's what I was showing you, the track of it. There is another structure of the small accretion disk there. Anyway, this is crazy busy. And if it wasn't looking busy enough for you, I'm going to show you this, because that red arrow is the distance between us and the Alpha Centauri. Our closest star, distance between us and our closest star. This is to scale. Everything I was showing you there of millions of stars, several million solar mass black hole, tons of structures, it's all fits approximately within a radius from us to the nearest star. This is a crazy dense region. Galactic centers are like this. They are like beyond our imagination. Like imagine million stars suddenly appear around us. That's the level of craziness in our life, which would happen if we lived in the galactic center. Yes, go ahead. The question was if I'm saying the singularity is the width of the solar system. No, I was saying that solar system is in the middle, and the distance to the closest star is marked to scale on this map. Yeah. Singularity is a singularity. We don't know what's the size. Is there any mysteries about the black holes? How much time do I have? Because I'm confused. Yeah, it's fine. Yeah, absolutely. Yes, where?
Online question is, how old is Sagittarius A?
Well, that's a black hole. We wouldn't know. So it is 4 million solar masses. Currently, it's eating gas with 10 to the minus 1 divided by 100 million solar masses a year. It's very small. So we usually assume that the black holes are formed approximately with the galaxy. So when the galaxy is formed, the black hole is formed, and the black hole grows with time. Whether this is true is not 100%, but the usual assumption is going to be it's forming together with the galaxy. So our galaxy is 10 to the 10 years, which is 10,000 and then another million, 10 billion years. So the black hole approximately the same age, but it's a black hole. It's not possible to date. You can date galaxies by the age of the stars, but you cannot date a black hole because, well, it emits what it emits right now. You don't know what the path was to this point. Okay. Are there any mysteries about the galactic center? Because obviously it is close by. We probably observed it to death, which is partially true, partially it's never enough. So are there any mysteries? There is actually, unfortunately, many. For example, that's a complex picture of everything in the galactic center. There is a S cluster of very young stars. There is another group of marked in purple of very young stars. And yet there is no star formation in the region. So, I mean, it clearly should have been somehow, and something should have happened so they're there, because the age of those stars is less than 1 million years. There is no star formation anywhere close to this region. So it's a big mystery how this happened. How is this cluster even there? How is this group of purple stars is there? Go ahead. So the question was that there is a lot of gas in this region, and so I made a statement before that there is no star formation, and the question whether this is possible that there is actually star formation because there is so much material. The answer is yes. So it's possible, but majority of the gas is at least 3 light years away. This red structure in the circle, right? This is molecular gas. So if star formation is happening, it's happening around there because that's where the gas is. if you make a star, like you have to launch it somehow to end up at the center. So yes, star formation in the galactic center is a complex topic. People fighting over it. People would say that I can see a bit of star formation here, a bit of there, but because the region is crazy complex, you need much stronger signal than anywhere else. So it's harder to prove because everything is moving. So yeah, that's correct. It can possibly, but not right in the center. And that's where the stars are. Exactly. So the question was how close is the sun to the center of the galaxy? From us to Sagittarius A star, I will go 8 kiloparsec, yeah. So there was this one. The passage of the star, you know how close. Yeah, it's 8 kiloparsec. Kiloparsecs, yes. Sorry, it's too many blinking. Any more questions? Okay. So, the paradox of Yoth, or sorry, you. I have an accent and there is nothing I can do about it. I also misspell and there is nothing I can do about it. So I mispronounce words and I'll do my best, but that happens. So, there's paradox, there are many young stars and almost no star formation. So there is also this thing which called variability crisis. So you probably seen this image. And you know it's a Sagittarius A star. So there are black hole physics is very complex because this image is actually model dependent. It's model dependent. It requires a model to fit the image because you have so little data. So what normally, so black hole physics is very strongly dependent on modeling. So why is it happening? Is like, this is, imagine like a schematics of normal physical process you want to study. You experiment, observe, doesn't matter. You have theory. You have simulations into which you put all of the theory you could think about and let it, interact with itself. Then it all feeds to your knowledge and you collect all this, you compare experiment with theory, with simulations, and then you understand the field. In black hole physics, it's slightly different. You have observations. You have observational data, which you then interpret based on your theoretical assumptions, which you derive from your simulations. You still put all your theory into your simulations, but you also feed your simulations into interpretation of the data. This is particularly true for the Event Horizon Telescope, because you cannot reconstruct the image with so few points unless you tell it what you're looking for. And while you can reconstruct the image based on the points, if you take the same model and you can ask the question, I have this model, tell me how much emission from the black hole varies with time, because you have everything, right? You just model the picture. You feed it, and turns out it varies way too much. So there is so-called variability crisis because the black hole itself is much less variable than any theory. Black hole is just much more calm. It's an approximate, it's like one of the simulations. It's very smoothly going. The black hole itself is on top, and the theory is doing just, and the simulation just doing jitter around it. And out of thousands of simulations, there is none which fits parameters the best, including imaging, variability, everything. So that's still an unanswered question. And the one I'm hopefully will also answer is the absence of active wind from the black hole. You know, why is the problem? Who cares, right? We see these beautiful pictures of black holes blowing jets. Like, why does our black hole supposed to blow any jets, right? So black holes always blow winds. There is nothing you can do about it for the following reason, is because when material getting closer and closer to the black hole and start radiate, that radiation pressure is a lot. The closer you get, the more of it you're getting. And that radiation pressure pushes away material at a high radii. So you're continuously kicking away the gas, while some fraction moving in, the other fraction being blown away. Particularly for this black hole, it consumes 1/10 millions of solar masses a year. But at the radius where you can calculate what's the wind, the temperature of the gas, thermal temperature of gas particle, or the gravity of the black hole, there is this radius called Bondi radius. It's a radius which gravity of the black hole does not let gas escape, because the gas at a given temperature can no longer escape this pool. So at this Bondi radius, the black hole captures 1 millionth, and then somehow loses 100 somewhere, because it blows them away with winds. So it is not possible to create a system where a black hole does not blow with winds. Moreover, matter, particles, gas particles. Oh, yeah. It's like you have a gas particles, and the gas particle have a temperature. If this temperature is high, then escape velocity or not. Well, the velocity associated with this temperature. That's it. And you clearly can draw it. If the temperature of the gas is different, this black hole size is different, it's going to be different. So black hole cannot not blow winds. Moreover, we know that our black hole did, because the blue line, I'm orienting everything like with other images I have. So the plane of the galaxies go like this blue line, which is our galaxy. And you see this huge gamma ray emission called Fermi bubbles. They are on a scale of the galaxy itself. So there is something was happening in the inside the galaxy close to the galactic center region that happened. There are also Rosetta bubbles, which is probably associated with the other ones. A little bit smaller scale, but still comparable to the size of the galaxy. On smaller scales, 150 parsecs, there is those X-ray chimneys. Again, great imagination. Bubbles, chimneys, etc. So X-ray chimneys, again, oriented approximately perpendicular to the galaxy. So we do know for sure that the black hole had outflows. But currently, if you look at this picture, you won't be able to see anything, because there is no obvious tracers of anything there. And that's my quick technical research part comes in about the discovery of the wind from the Milky Way center black hole. And so I'm pleased to announce, and I hopefully in the next 5 or 6 slides, I'm going to convince you that there is a wind from the black hole. And that's worked together with Mark Gorski, who was my postdoc and our research professor at Northwestern. Despite his last name, he's a man. And no, he have to explain that he is not Polish. He's American. His grandparents are American. He doesn't speak Polish. Anyway, so let's work with Mark. So to explain you how exactly we discovered winds, I have to tell you 3 short stories. One about reimagining good old data analysis technique. The other one about finding something people will forgot about for 30 years. And then finally finding the solution to the 50-year-old puzzle, which, disclaimer, is the wind, because it was first claimed it should be there about 50 years ago. Now I have a question. How many of you are familiar with interferometry? Please raise your hand if you are familiar with interferometry. Okay, I will very quickly mention what interferometry is. So interferometry, interferometric telescopes in general is a combination of separate telescopes where you correlate the information between them. This is a hand wavy, I mean, that's correct what I said, but it doesn't probably tell you anything. Now imagine the following. Imagine you have a normal telescope. You have a very big lens. You're collecting light from all of this lens. And now you throw a piece of fabric on top, which only has several holes. You collect information from those holes, and you try to reconstruct the image. So obviously, it's much harder for you to do this. Moreover, that part is a bit technical. Radiation which falls from a distant object to the surface of your lens is a Fourier transform of that object. The same thing falls into your eye. The eye and the lens doing inverse Fourier transform, so it forms the image back to you. Interferometry, because you have these little dots and you only collect information in the holes, you have to do it on the computer. There is advantage of interferometers. They can be really big. This is one, which is Event Horizon Telescope, the whole size of the whole planet. But also, they have big disadvantage. And disadvantage is because it's so complex what you have to do with your data. Your response of your telescope to even a point source, like one star, is going to be much more complex than you used to. So interferometer, it depends on the configuration of the interferometer, so the particular configuration will change. So this image you have on the left, and I'm not sure how bright it is, but you see a pattern, like lines going all over the image. This is a response of interferometric telescope to one bright point. All of that. Again, it might be hard to see because it's easy to see on my screen. I'm not sure it's easy to see there. The image on the right from you, also on the right from me, on the right, has it's press release image from 2021. It has exactly the same pattern all over it. Just because this is hard to deal with, because every single point source get you this. And this monstrosity is hard to subtract. So cutting the long story short, and I will not scare you with the next slide. So big issue here is because your Sagittarius is the brightest source on the image. It sends you this enormous artifacts all over it. Moreover, telescope rotates with rotation of Earth. And it's a variable source, meaning it's spreading you these artifacts with different strengths, depends on the angle you're rotating. So it's very hard to deal with. Anyway, we figure out how to deal with it by changing the steps, not the imaging steps, where usually people try to improve it, but changing the calibration stage. Because you have to calibrate on a variable source, and then you can subtract it. Anyway, I'm skipping the next slide because it's scary. And going directly here. So first thing we did when we applied this technique to something known, and this is a section of, this is a section of the mini spiral. It's the same thing I showed you about a little bit earlier. So this is you see how the contours piling up on the edges? There is no thick lines on this plot. It's just a very clear distinction between the gaseous structure and whatever is behind. They just lines are piling up because it's like, so every single dot here is real. Every single dot is a 10 sigma. And by the way, the resolution is going to appear on the screen right now. That little dot red now at the end of the image. So every dot you see here is real. It also perfectly fits all the known data except with high resolution, so we knew it works. So how does it bring us to the next point of applying it to something people got for 30 years? In 1994, Marshall and Lazenby, whose name not necessarily have to be familiar to you, two astronomers, observed CO molecules on the Galactic Center. They observed transition 2 to 1, which is a very low transition, and CO molecule in general is a very good molecule because it's the strongest chemical bond known to nature. These molecules survive from small, very, very low temperatures to very, very high temperatures. And it probes your molecular gas really well, everywhere. And so that's a really good molecule. Anyway, so CO2 to 1 is very low transition, meaning it's very valuable if you can get information out of it. It probes you about 100 Kelvin, which is molecular gas, particularly good for molecular gas. Anyway, so Marshall and Lazenby in 94 observed this line with not particularly good telescope, not particularly good resolution, and concluded that you cannot see it from the Galactic Center. Since then, every proposal proposing to observe this line from the Galactic Center has been denied, referring to Marshall and Lazenby, 1994. Luckily for us, we had the same line, which was in the data, which was not targeted. It was just on the side. And so we actually had it, and so we imaged it. Because it's a very bright line, and if you can, like, oh, thank you so much. So what we saw is like, something which looks like inverted butt. The bird, the animal. Anyway, so this thing, which obviously may or may not be true. We'll show you that it is true because I would compare it all the known structures, particularly the one with the color. The molecular ring is known and studied to death. The field of view we have is very narrow, it's just like one parsec, but it fit into it as a glove. Identical 1-to-1 in the bright points, except you also see everything inside. You can see also some other structures, which name is not supposed to be familiar to you. It's just some structures in this region which I also know. So we knew this thing is real. So how do we solve a 50-year-old puzzle? Is by staring at the picture a little bit and figuring out there is something absent on it. A conical structure is absent on it. The plot on the right might be a little bit confusing because I also draw these conical lines there, and you can see there is very little emission, but very chaotic velocities of that emission, which means there is something happens there, but in principle there is very little things happening. So interpretation of this, there is a huge flow of 45-degree opening angle going right through this molecular gas and carving a hole. Moreover, if I overlay it with a mini spiral, turns out the third arm of the mini spiral, it is here, it starts exactly the same place where the jet is supposed to hit it. It has long been debated that the third arm of the mini spiral is not the gaseous stream, but ionized substructure on a molecular ring with something ionizing it. Somehow direct with a direction. And, it's just a pretty picture on the right with molecular gas overlaid with X-rays, where it's also kind of obvious that you see the structures in the X-rays which are filling the hole. It's also obvious that it's anti-correlating with molecular gas, which is natural because hot and cold gas not supposed to like each other. If you have more X-ray emitting gas, you have less cold molecular gas. Anyway, so the conclusion is that we did indeed find the wind from the Milky Way central black hole. It's in a weird direction and it's not perpendicular to the plane of the galaxy. If someone asks me a question at the end, I can tell you why I think it's perfectly normal. I'd like to say that the wind was proposed in the 1970s by Lyndon Bell, who was a British astronomer, and found 2025 by, well, me and my colleague. And during today's lecture, I tried to explain many things, and I probably badly run out of time. So we talked a little bit about the black holes. We talked about the importance of black holes in the universe. We talked about Milky Way's center and how complex it is. And then we talked also about the wind from the black hole. And with this, thank you so much, and please ask questions. Thank you for asking this question. So when we assume that the wind is supposed to be perpendicular to the plane of the galaxy, what do we rely on, right? We rely on seeing the galaxies with something coming out perpendicular from it. Well, imagine you have something which is blowing you wind not perpendicular to the galactic plane. Your only escape direction is still perpendicular to the galactic plane. You cannot escape any other direction. So it is interestingly, so you normally would think about this and it's like, okay, galaxy here, it's everything rotates like this, so the black hole should, and it's reasonable, but then you stare at the galactic center, look at the obstructions, you understand nothing aligns with anything. Which one is supposed to be preferred direction? There is no preferred direction. And so then you see a jet also going not preferred direction. You just like, that's a big mystery why, but at least we know now that they're not supposed to go perpendicular, because for the galaxies we actually see it, in the majority of cases, they do not go perpendicular to the plane. The question was whether poles of the black holes, which is the direction of the black hole spin, is not perpendicular to the galactic plane. Yes, it probably would. Yes, it does. Like, it doesn't have to be oriented perpendicular to the galactic plane. Quite interestingly. The question is whether the stars very close to the black holes have planets. Probably no, for the reason is that's very dense, right? They're passing by each other really, really close. So the planets, for them to form and stay bound, there are definitely free floating planets in the galaxy, right? But to have a planet, which I think what you mean is having a planet bounded to the star while they're doing this would be quite unlikely. The question is if we looked at the polarimetry of the jet, because we're looking at the radio. No, we haven't looked on this because it's a combination of existing data which was requested for primary. The primary science was not that science. And the observation were requested non-polarized. You cannot get polarized information from non-polarized request because then they would not carefully calibrate, so it doesn't contain this information. Sorry, say it again. So the question whether the stars rotating in the galaxy around the same way as the planets rotate around the sun. The answer is they are rotating in a plane, so it's in a way correct, but they're not rotating with sun is a central mass with a potential 1/r. It's like Keplerian potential. For the stars, it's not going to be the case because there is first dark matter and also there are many more other stars. So there is not a single dominant mass which holding it together. It's a distributed mass. So the question if our black hole unique or is similar to the galaxies, the black holes in other galaxies. So generally assumption in physics and astronomy that nothing around us is unique because it would be very hard to justify, right? So our black hole is on a small size of the black holes, which can happen in other galaxies. It's also in the state where it is underfed, meaning it has very little material to it, which is believed to be the dominant state of the black holes in the universe. So they do fireworks for a short period of time, and then they kicked away all the gas, and then they sit in there waiting for something else to come. And it's usually they have this very bright moments of life for a very short period of time, and then they sit in there being boring and doing nothing for majority of their life. So it's not unique in this way. The only way it is unique is we know most about it. I mean, when Mark brought this picture with the thing, and there was a rotation, and we were just like staring at it, and it's like, this thing is conical, right? Because like it's not primary science. So normal procedures to cut this frequency often throw it away because 94% that's what we were doing. And then we saw something on the edges of what we were throwing away, which was known. We knew there is an edge of the molecular ring was coming through, and we saw it exactly as it was supposed to be. And so we decided to image it. And then this thing came out as like, oh, guess well, it's going to be a long battle with a referee.
you so much for a really wonderful talk. Thank you so much. And
So long because I definitely know that I much longer.
yeah. Can you stick around for a little longer for people have questions? Yeah. She's able to stick around for a little longer if people have questions they want to ask her that didn't get asked in this. And thank you all for coming. And I hope you all have a wonderful month. And we'll see you in April.